All right, so today we're going to take a look at Newton's second law. So our last video finished with Newton's first law. What are your takeaways? So make sure before you start Newton's second law, you go back and you look at Newton's first law and the kind of the four key takeaways there. All right, Newton's second law. It says, well, there's several parts to this. It says first off that a force is a push or a pull. So if you've ever thinking in your life, if you're playing a sport, basically you can push or you can pull, and that goes with even something like if you're a football player and you're blocking somebody, well, you can move them, you can push them, you can pull them. If you're playing baseball, when you hit a baseball, it's basically put a push onto a baseball, you exert a force. So Newton says a force is simply a push or a pull. Another thing you have to know about a force is that it's a vector quantity, which means that direction is going to be important. So if you push something, the direction is going one way, and if you pull something, the direction is going the opposite way. And then forces are measured in newtons. Those are the SI units that we use in physics class. And then in our daily lives, a lot of times we use pounds to measure forces. And I just put this little graphic from our physics book over here, but you can see here there's this purple object, and it says you have a 5 Newton force and a 10 Newton force, and they're both going to the right. And so if you have two forces and they're going in the same direction, these two forces, just like when we talked about vectors, those vectors will just add together. So we'll say your net force, which is just a fancy way to say like your resultant or your total force, would be 15 newtons to the right. And then just like when we talked about vectors before, if you have 5 newtons going to the left and 10 newtons going to the right, then your net force, you just subtract them. And then you could have the case where you have two forces, like you have 5 newtons here going to the left and 5 newtons going to the right, and then the net force in that case would be 0. So when we talk about forces, we can think back to when we were doing vectors, and because forces are vectors, all that math with like SOHCAHTOA is going to come back to us. All right, the big thing about Newton's second law, it's basically this equation right here. So it says force is equal to mass times acceleration. So if you wanted to say what Newton's second law is, it's basically this equation right here. So the Newton's first law was a lot of words. Newton's second law, just one equation. Another way to say it is, in other words, a mass will accelerate or change velocity when a net force is applied to it. So going back to these pictures here, if we look at this first one, the net force in this object was 15 newtons to the right, which means that that object is going to accelerate to the right. What that means is if you accelerate, that means you're going to be changing your velocity. So this object, if it has a force on it, is going to start to change its velocity to the right. The object below it, 5 newtons, will also accelerate to the right, but it'll be just accelerating at a lesser rate because 5 newtons is 1/3 as great as 15. And then if your net force is 0, that means there's going to be no net acceleration. All right, so Newton's second law, the equation, F equals ma. So if you ever see that written down, that's Newton's second law. F is force in newtons, and then we'll talk about what a newton is in just a second here. But F is force in newtons. M is mass in kilograms. And you got to be careful because if they ever give you a mass that's in grams, you have to convert it to kilograms. Otherwise, it'll kill your grade on a test. Physics teacher joke. And then you have A, which is acceleration. And that's going to be in meters per second or meters per second squared. So the question at the bottom says, what is a newton? Well, if we look, if you remember, mass is measured in kilograms. So I'm just going to say mass is measured in kg. So when we actually multiply mass times acceleration, you also multiply the units here. So mass is kilograms, and then acceleration is measured in meters per second squared. So if we look here, when you measure mass, when you multiply mass times acceleration, that means your units for force would actually be what's called a kilogram meter per second squared. And then scientists back in the day decided that that's a little confusing, that's maybe a little clunky to write after all of your force problems that it's going to be a kilogram meter per second squared. So what they did is they said, hey, Isaac Newton came up with the concept of forces. Let's just define a kilogram meter per second squared as 1 newton. So then we'll just say 1 uppercase N for newton. So when we do force problems, we just say the force is measured in newtons. All right, so let's take that equation for a spin. So it says, number 1, what acceleration will be produced by a force of 4,000 newtons acting on a car with a mass of 1,000 kilograms? And this is Mr. Laurent's dream car right here, Ford Mustang. And I'm actually going to change it. I'd like the convertible version of this car, but Go ahead, hit pause, try this problem out, and you're going to do given want equation numbers and see what you get. All right, we're back. And if you look, our givens were not too bad. We just had two of them. We got our force was 4,000 newtons and the mass is 1,000. We're looking for A. Well, you only have one equation that has an F, M, and A. It's Newton's second law, F equals ma. So you just solve that bad boy for A. So it's going to be 4,000 newtons divided by 1,000 kilograms. And then you'll get that the acceleration is 4 newtons over kilograms, which that's what your units would be based on what you see here. But then you could just remember back is that acceleration is measured in meters per second squared. All right, so that's not a bad one. Let's try a little tougher one. Newton's second law, example 2, the space shuttle Atlantis, which they actually have at the Kennedy Space Center near Cocoa Beach, Florida. They have the space shuttle on display there, which is really cool if you ever get a chance to go down to Florida. So here's the question. It says the initial mass of the space shuttle Atlantis is 2,040,000 kilograms. Calculate the thrust force needed to accelerate the shuttle from rest to 44.8 meters per second or 100 miles per hour in a time of 8 seconds. So basically in this case, we're looking for the force, the thrust force that's needed to accelerate this rocket. So you're going to be using Newton's second law and one of our old equations from our previous unit. So go ahead, hit pause, try this one out. There is a bonus question down there at the bottom, so try that one too. All right, so if you had a chance to attempt this one, we're going to show you the solution in just a second. But the bonus says, after the first minute of travel, more than 1.5 million pounds of fuel are used. How does this impact the acceleration of the shuttle? So we'll answer that one in just a second. But here's what the solution looks like for our space shuttle problem. They give you the mass, and they give you that it starts from rest, they say. So that means that VO is 0, and they tell you that it gets up to 44.8 meters per second in a time of 8 seconds. So we say we want F, our force, thrust force. The only equation we ever have to get force, in this case, the only equation we have is F equals ma. So let's say to ourselves, we need to get A. So we're going to go back to our equations from 2 units ago, and we're going to say, well, our equation for acceleration is just V minus VO over T. So there's just one extra step in here where we're going to use that equation to calculate the acceleration of this rocket is 5.6 meters per second squared. And then once we have our acceleration, we just plug it in right there for A. So in this case, you take 2,040,000 kilograms times 5.6 meters per second squared, and you get 11,424,000 kilogram meters per second squared. And then we remember that, that's just equal to what's called 1 Newton. So our final answer would be right down there. It's about 11 million newtons worth of thrust force. All right. So the bonus question we'll go back to, it said, after the first minute of travel, more than 1.5 million pounds of fuel are used. How does that impact the acceleration? Well, to do this one, you're going to look at the mass of the space shuttle and basically this whole kind of rocket system here. If the mass is going down, but the force is staying the same, because the force of the rocket engines propelling upward are the same, that means that the acceleration is going to be increasing. So that means it's going to be continuing to gain speed at different rates. Basically, the acceleration will be increasing. That's why it looks like the rocket's going faster, faster, faster as it goes up, because it's losing mass. It's kind of like if you're carrying a whole bunch of things as you're jogging, and then as you're jogging, you started to drop those heavy things. As you lost mass, your acceleration is going to increase. All right. So we did an example there. The last thing we're going to talk about today is the concept of net force. So here's Newton's second law again. And technically, when we do the second law, I should be writing this phrase or this word that says the net force. And the reason why is because that's like saying what's the overall force on an object. So let's look at a couple examples. It says, what forces act on a piano that's sitting on the floor at rest? What is the net force? So here's a piano, and just go ahead and hit pause. What are the net forces acting on a piano that's like at rest, just like sitting in somebody's living room? All right, so for this one, I'm not going to try to draw a piano, and that's an awful floor right there, but let's just say that you have the piano there, it's just a block. Well, what forces are acting on that block? We know that the force of gravity is acting down on that piano. And in physics, that's something that's called an object's weight. So the weight of that piano is acting down. And then the question you have to ask yourself, is that the only force that's acting on that piano? And the answer is no. Because the piano is on the floor, there's a force from the floor that's going up. And that force is actually the same strength as the weight of the piano. And this might seem a little strange, but we're going to use an uppercase N. And that's what's called in physics the normal force. It's basically a contact force from the floor. It's like a support force that just acts up on an object. And in this case, we have two forces acting on this object, but the net force on that piano is 0. And since F net is 0, if we look over here, we know the mass of the piano is not 0. That must mean the acceleration of this piano is 0. So that means that piano is not going to be accelerating in your living room. Now, that doesn't mean the piano is not moving. It could be moving, it would just be moving at a constant velocity. But my guess is that if you have a piano in your living room, the acceleration is equal to 0, and your velocity is also equal to 0. All right, let's try this one. When moving a piano, Bill pushes to the right with a force of 200 newtons, and Ned pushes to the right with a force of 300 newtons. What's the net force on the piano? So we're going to draw a picture of this situation again. So there's our floor, our shaky floor. And again, even though we have Bill and Ned pushing on this piano, we're going to go right to the middle and we're going to say the force of the piano going down is the weight of the piano. And then the force of the floor is still acting on the piano because we're assuming they're sliding this piano across the floor. So there's the force of the normal force going up. And now in this case, when moving a piano, Bill pushes to the right with a force of 200 newtons. So we're just going to say to the right, boom, is a force. And let's just call it, I don't know, let's call it F1 because it's the first person pushing. And Ned pushes to the right with a force of 300 newtons. So we're going to make this vector just a little bit longer because that is his buddy Ned, and that's going to be the force from the second person. So in this case, these two vectors are aligned. So if you remember back to our vector unit, when you have vectors like this, you don't have to use SOHCAHTOA, you can just add them up. So your force, your net force, is going to be 500 newtons. And sorry for the bad handwriting there, but it'll be 500 newtons, and we'll say to the right because it's a vector. You have to put the direction in there. So basically your forces in your up and down y direction cancel, and you have a net force going to the right. Or you could say x direction. Or if you're thinking like a physics all-star, you could say x hat direction. Cool? All right, we'll finish with this right here. Newton's second law, F equals ma. A few years back, I had a student say something like this to me. Mr. I saw this shirt that says, may the mass times acceleration be with you, and I didn't get it until after today's lesson. And I'm like, well, for copyright reasons, I can't take credit for this image here because that's from Star Wars. But may the force be with you is the expression. But we now know that force, according to Newton's second law, is mass times acceleration. So that's why if you've seen those shirts, may the mass times acceleration be with you, it's basically somebody geeking out on the fact is they know what Newton's second law is. So when it says, why have I seen the shirt that say may the mass times acceleration be with you, now you can be part of that exclusive club as well. So you can say may the mass times acceleration be with you. All right, thank you for watching. Have a wonderful day. Go Physics All-Stars.